I also am pretty big into the meetup community as well. So I started last year a group called Toronto AI. Anyway, we do some pretty cool events. We've got one probably coming up for the 20th, so keep an eye out for that. Yeah. So in terms of my background, I'm a machine learning engineer at a company called Recurrent. And then I am also just really big into AI. So like if you want to ask me about AI, specifically generative adversarial networks, that's kind of like one of my favorite areas. Yeah, anyway, that's...
I have a quick question. Sure. So what do you feel the difference between this meetup group and the Toronto AI?
That's a good question. The Toronto AI tends to be a little bit less specialized. I would say that's probably one of the main differences. Like here, the audience is quite a bit more technical. With Toronto AI, it's a little bit less technical. Yeah. Okay, so thanks everybody for coming out tonight. So anyway, we're going to do a discussion here on Eve. And it is a gradient-based optimization method with locally and globally adaptive learning rates. And the interesting part about this is the globally adaptive learning rate and their approach to it. And so the link to the paper is there. Let's take a look at the authors here. So these are the three authors of the paper. We've got Jayanth Kaushik, who is a PhD student at Carnegie Mellon University. His H-index is 4. For those of you who are not familiar with the H-index, what that means is that he's had 4 papers that have been cited at least 4 times. Graham Neubig, H-index of 26, so he's had 26 papers that have been mentioned at least 26 times, or referenced at least 26 times in other papers, right? And so he's an assistant professor of CS at CMU. And these are the Twitter handles there. And then Hiroaki Hayashi, that's his photo from Twitter there. He's also a student at the CMU as well. And so this paper, it's equal contribution from Jayanth and Hiroaki. Okay. The link is, yeah.
What made you think to put the H-index up there? What was your assessment of seeing their H-index indices that made you think that was, made you think to put it up?
The way that I interpret this is that this person essentially, like just going from the names, there's not much information. There's really no information there unless you happen to recognize the person. But from this, we can see that Graham Neubig was essentially supervising the paper. That's, yeah.
The picture by Hiroaki Hayashi is of a fractal in nature. It's in a lot of Benoit Mandelbrot's work and papers. So similar, the waves and the water. Yeah.
That might be part of the reason why he chose it for his Twitter image, but I wasn't able to find an actual image of Hiroaki, so that's the closest I could find. Okay, all right, so Eve, Adam and Eve. So actually, this is a picture of Adam and Eve in the Garden of Eden by Wenzel Peter from Carlsbad, 1745 to 1829. We're not going to be talking about that Adam and Eve today, but we are going to be talking about Adam and Eve, the optimizers.
Is that one that was recently found that was lost?
I have no idea. I think this one looks familiar to me, though. I'm pretty sure I saw this when I was like growing up, though. So you could be right, though. Anyway, it's a great painting. Okay, so let's get into some of the basics here. So we've got a neural net. They don't have to be in well-defined layers. You can have like any differentiable model with, I mean, you're allowed to do that. So you've got your data that you want to feed into the neural net, and then you've got your prediction. And what we're indicating here is that we're just going to indicate the prediction by putting a little hat over the y. This is like the prediction, and we're saying here that the prediction is with respect to the parameterization of the model. So this model can be described by parameters theta, and we're saying that this prediction is a result of passing x through the model that was parameterized with theta. Okay? So we're just covering a little bit of notation here. And so we can say that the neural network itself is just a function of x. And again, here we're indicating that f is parameterized by a set of parameters that we'll just call theta. Okay. One thing to keep in mind too is that typically with a neural network, for every neuron, there's usually there's a weight associated. There's a set of weights associated with it, right? And so the number of parameters that can go into a neural net can range from a very small number to the large end of the scale, billions. So this can be this is a very convenient way to summarize simple or extremely complex things. Okay, so this is our model so far that we've defined. We essentially have a function of x parameterized by theta that gives us our predictions. Okay, and so our goal, and we're going to be talking about these optimizers within the context of a supervised learning problem, but there's really nothing tying this to supervised learning. These optimizers can be used for unsupervised learning because the optimizers only really care about optimizing a loss function, and it doesn't know whether or not your loss function is based off of supervised labels or if it's based off of other criteria in an unsupervised learning problem. So, but in our case, just to keep things simple, we're going to talk about a supervised learning problem. And so our goal here is to essentially take our predicted values, those that we just introduced, to the ground truth, which we'll indicate as y there. So we want this to converge to our predictions to converge to the ground truth. And so the gap between our predictions and the target is what we call the loss. And the loss is what we want to optimize. We want to minimize the loss, because as we minimize the loss, our predictions approach the truth, or the ground truth, however we've defined that. Okay. So there's many different types of losses. Mean squared error, cross entropy, pairwise distance, hinge loss, pullback, Leibler divergence, Poisson loss, cosine proximity, Huber loss, and an endless variety of others. You can just create new loss functions as needed. These are some of the more popular ones. I'm sure you could name a number of other fairly popular ones just to add to that list. So we don't really care about the specific way that we're measuring that loss. All of these, by the way, just to rewind here, all of these loss functions are different ways of measuring the gap between your predictions and the ground truth. So it's like there's a gap between them. How do we measure how far away we are? Because if we can quantify that, then we can minimize it, assuming that it's posed in a differentiable way. So the specific type of loss function doesn't really matter as long as it's differentiable, and so we can just refer to it as L. And again, we're going to say here that the loss function for our particular problem is parameterized by theta. We're just keeping in mind that it's with respect to a particular parameterization of the network, that given our predictions and given the true values, we can then measure the distance between them. Okay, and then given our loss function, we want to be able to minimize that distance. Okay, so yeah, rephrasing our goal, we want to update the parameters of our model to find parameterization that minimizes the measured loss, which is our distance from the target. And so by minimizing the loss, our predicted values approach the ground truth labels that we've provided. Okay, so we're slowly building things up here. So that's our loss function. Let's now talk about stochastic gradient descent. This is the basic approach for optimizing a loss function. So this is an iterative approach, and so we have the parameters of our model at the next time step set equal to this bit here, and we'll describe that. So the parameters at the current time step, we can consider that to be our current position in parameter space. Those are the weights and the biases that are inside our model, whether it's a neural net or other differentiable model. The step size, that's our learning rate, also conventionally alpha in a lot of the papers. That's usually the most important hyperparameter of any particular model, is how big of a step should we take in parameter space. And then this green area here, this is our step direction. And that direction is the gradient of the loss. And so we'll cover what that is. This is going back to some calculus. So many of you probably have a good understanding of this already from, we've got a lot of people actually here with backgrounds in math. So the gradient is essentially a direction in this case, in parameter space. And that direction would point uphill with respect to this particular loss function here, or with respect to the parameters of that loss function. So uphill being regions of higher loss for this function. And so because that's pointing uphill, we say we want to take a step downhill in the opposite direction. And so in doing so, we head to lower regions of loss. And that should hopefully bring us closer to the ground truth, to parameters that result in lower loss, which means by lowering loss, we're minimizing the distance between our predictions and the ground truth. Okay, and so our current location, adding on to that our step in a direction, so our step size in a particular direction, gives us our new position in parameter space. And then we just iteratively apply that algorithm until we minimize the loss sufficiently for our purposes. So if we want to take a look at what that's like, if we look at that in one dimension, here we've got the minimum loss for this particular function. So we've defined a loss function. We'll say that it has a minimum L star, and we can see that that's at the bottom of a valley here. And so when we start our model in parameter space, we're just talking about a model with one parameter in this case, is going to be somewhere on a slope. And that slope is going to have a direction uphill and a direction downhill, and that's essentially our slope or our derivative or our gradient. And so then if we refer to that gradient or that slope as with our symbol there, then we can essentially take a step that is in that direction by the size that we've set for our learning rate. So we can tune alpha up and down to take larger or smaller steps. And the idea is that if we take a step in the direction downhill, we'll move closer towards the loss, the minimum loss. So this is just with one parameter model. So a simple one parameter model that you guys might be familiar with, like y equals mx plus b, where m is the parameter for the model, and b could be a bias. That would actually be a second parameter for our model. So let's just say y equals mx as a really simple example. Or another approach, let's say y equals mx squared as another potential model with one parameter in it. Okay, so in parameter space, we normally deal with multiple. We normally have models with multiple parameters. So if we go from one parameter to two parameters, then we start to look at situations like this, where our loss is no longer just a hill. Instead, we're starting to create a loss landscape. And so eventually, you could imagine that this is going to be more and more difficult to visualize as we go from two-dimensional representation to billion-dimension representation. Obviously, we can't do that, but this gives us kind of a good idea as to how to start thinking about some of these problems. So as we perform stochastic gradient descent, there's the formula there in the bottom. Essentially, what's going to happen is that we're going to start moving through parameter space. In this particular case, the minimum loss is the center there. We're going to start moving through parameter space via this stochastic gradient descent optimization approach. So we can consider our optimizer here to be stochastic gradient descent. we're going to start taking steps, and those steps are going to depend on the gradient. So the gradient contains actually two pieces of information. It contains the direction, but there's also, because it's a slope, that slope can be large for large slopes and small for small slopes, or like steep areas are going to have very large gradients. And so what we'll find is that we'll start taking steps that are quite large in areas of high gradient. And in areas where things are shallow, then our step sizes become much smaller. Okay, so we'll end up seeing something like this. Okay, so it's not really quite what we wanted here. So in this particular case, if we were to trace out essentially what would happen with stochastic gradient descent, and obviously this is just a visual approximation, I'm just trying to highlight what can go wrong with stochastic gradient descent. Here we've got a situation where B is our parameter B, theta B there, where that refers to one particular parameter, is taking steps that are too large that are oscillating around the ideal value. So if we look on the theta B axis here, our ideal value is right about here, but we keep taking steps across that ideal value, and that parameter is having a really difficult time converging. At the same time, our steps, because we've got this like valley, because we've got this area where there's a mismatch in the gradient depending on the direction, right? It's not perfectly spherical. We've got more of an ellipse-based shape here. So there's essentially this trough of like high gradient where our theta A parameter is not taking large enough steps. So even though it's probably like when it eventually reaches the minimum, it's probably going to hit that right on. It doesn't look like it's going to overshoot it like theta B is, but it's going to take a really long time for it to actually arrive there. Okay. And part of that is because there's not much gradient pushing it in that direction, but that's where it needs to go. So yeah, so we have a case here where theta B, the steps are too large, theta A, the steps are too small, and so our convergence is taking much longer than it should. Okay, so how do we improve this? So one key observation here is that different step sizes are appropriate for different parameters. Like it would be more appropriate for theta B to take smaller steps, and it would be more appropriate for theta A to take larger steps in this case. So it depends on the particular situation. And so that brings us to a solution here, which is essentially to do exactly that, to give each parameter their own learning rate. And that brings us to the Adagrad family of algorithms. We've got RMS-prop, AdaDelta, and Adam. And Adam is the most popular. Actually, RMS-prop is really popular too. But that family of algorithms is very popular. Adam is a very, very popular optimizer to use. And it performs really, really well. Okay, so yes?
If you mind, bother with this, but I remember RMS-prop and Adam. I don't quite remember AdaDelta. I just want to refresh my mind before going further.
Yeah, so AdaDelta, I'm not sure. It's just part of the Adagrad family. So RMS-prop is like a simplified version of Adam, but
yeah. So
okay.
Does anyone know?
Does anybody remember AdaDelta?
AdaDelta.
You know the math and everything. You didn't think that was punch you?
No, I have to check AdaDelta, what is in it, right? I said you can throw questions, but I will do. RMS is root mean square propagation.
Yes, yeah, Adam is RMS-prop plus the other one.
Yeah, I check for AdaDelta and come back. Sure, thank you.
Yes.
So for this particular problem,
Can you speak up?
Yeah, so for this particular case, like, could you just rescale the parameters and solve the issue without having to do adaptive learning?
So the question here is whether or not you can rescale the parameters
if this is the problem that you're
change the
trying to
landscape. Now, one of the problems with this is like what we have access to be able to modify, right? We have our optimization approaches, which allow us to update the weights, but I think what you're referring to is there something that we could do with the data maybe? to change the loss landscape. And yeah, totally, you can. If you,
Yeah, I just mean like rescaling the feature itself.
yeah, exactly. So if you look at a neural network layer and you take like when we talk about finding the slope of these parameters, so the slope for theta A here, if we look at it here, it's generally shallow over, or yeah, for theta A, it depends on like the loss landscape with respect to the other parameters, right? If you look at measuring the slope though, with respect to a parameter, so the gradient of the loss with respect to weights in the network, the answer is not going to be in the weights. It's going to be actually the data itself, right? So it's like if your loss is equal to some function of the weights and x your data, then that gradient is going to be specified in terms of x, not in terms of the weights. And so by modifying the data, by modifying the data itself, so like performing various approaches for normalization, you can create a much more friendly loss landscape. And so that can be pretty helpful in situations where you have the ability to do that. In some cases where, for example, if you're looking at like image recognition, it's difficult to know what to do with the data to be able to smooth things out at each different part of the neural net. Because I mean, there's millions of parameters, and they're exposed to like all different kinds of gradients from like derived features and so forth. And depending on at what point in training, it's like one of the key points, and we'll talk about this in a bit, is that the loss landscape is always changing. And anyway, but for simple problems where we're talking about, say, a classifier based off of a table of data, then if you've got one feature that has data within, say, like the normal range, and another feature that has data in a range that is on a completely different scale, then it definitely helps. It should help to normalize that. But again, this is something that you should verify empirically, because sometimes normalization of data will actually cause detriment to the model. But it really depends on the case. Yeah.
So I looked up AdaGrad and AdaDelta. Apparently, like AdaGrad is the one where you the learning rates are proportional to the sum total of squared gradients.
Yeah.
Since the beginning of history, AdaDelta is just like an exponentially good thing.
AdaDelta.
Cool. That sounds very similar to, like, you're going to see echoes of that in here.
So this is basically Adam. So Adam adds the gradient in the numerator. So these guys are just like modifying that. So
yeah, yeah.
Is like the different algorithms only focus on changing the step size, or is it a good strategy to also think how the loss function itself is built in?
Yeah, so we're not actually going to talk about modifying the step size itself, but this would now be a really good time to actually talk about that, since you brought it up. So in these algorithms, what we're looking for is a way to modify essentially this term that's used to update the step. And so effectively, it's modifying the step size. I think what you might be referring to here is the learning rate, and that's one component that determines the ultimate magnitude of those steps. So there are approaches where you can, for example, decay the learning rate over time. That's pretty popular. So there's a couple of approaches to that. So say at t time steps into training, you could essentially decay the learning rate to 1 over t, or 1 over the square root of t, or e to the negative t. There's just all kinds of strategies around that. And then you can also apply, so it goes even further than that into cyclic learning rates and various approaches in that space, where instead of having a learning rate that is decaying at a very predictable, continuous, well, I guess it would still be continuous in both cases, but instead of having a learning rate that is just very gradually decaying, instead what you can do is cycle that learning rate to go from slow training to high training to slow training. And so there are benefits and there are papers around that. And so I would definitely encourage looking into that as well. That's, but yeah.
So is it very different from simulated annealing, where you kind of keep changing the learning rate to find your optimal basin in the landscape?
Yeah, so essentially that, like, putting in a decay term onto the learning rate itself is simulated annealing. And then in terms of some of the, like, well, yeah, let's just leave it at that. Okay. All right. Okay. So this was our stochastic gradient descent update rule. So again, we're just going from our current position parameter space to our new position by taking a step in this direction that is magnified by the learning rate, whatever we've set that to. And yeah, the direction is downhill toward lower areas of loss. Okay, so let's just simplify the notation a little bit here. Just allow me to do this. We'll refer to this as the direction. Okay, so what Adam does is it modifies things a little bit. And so I've been a little bit untechnical here by describing it in words. So essentially, we changed the update rule from taking a step in the direction directly downhill to a direction that is proportional to the average recent direction, and then inversely proportional to the average recent deviation in that gradient. And so let's start to unpack that a little bit. Okay, so what do we mean by unpacking, or so what do we mean by average recent gradient here? Okay, so stochastic gradient descent always takes steps in the downhill direction based on its immediate local position in the loss landscape. But as we've already mentioned, the loss landscape is noisy. So the loss landscape in parameter space that the optimizer must navigate through totally depends on the input data. The loss depends on the predicted values, and the predicted values depend on the training data. And so since our input data changes with every batch we send into the network, so does our loss landscape. And so instead of it just being a smooth problem of head downhill to the bottom, instead we've got a landscape that is constantly in flux. But there still is a minimum out there, and we need to find a way to reach that. So Adam attempts to cancel this noise by adding momentum to its trajectory through loss space. And it does this by heading in the direction based on the running average of recent gradients, instead of in the direction of the current potentially noisy gradient. One way to think about momentum is if you think of a ball rolling downhill, right? If that ball is a ping pong ball, it doesn't have a lot of momentum. And as it's rolling, it might hit a rock and bounce off in a direction that is not ideal. And if we look down at that level, all of the individual rocks are going to essentially cause problems and cause that ping pong ball to bounce all over the place, when all we're trying to do is just to head downhill. If we add a whole bunch of momentum, say instead of it being a ping pong ball, we change it to a boulder and essentially send that down the hill, it's not going to care about those small bumps along the way, essentially. Okay, so we can rephrase this to essentially say that we're using the momentum we're using momentum, and so our step size is proportional to that. So if we think back to our ping pong ball analogy, it might be taking steps like this through parameter space, whereas when we add momentum, it smooths everything out, Adam here being the red arrows, and stochastic gradient descent being the noisy updates that we see there. It's not that gradient descent is noisy, it's that the landscape that it's moving through is noisy. And so we can mitigate those effects by adding in some momentum. Yeah, exactly. It smooths out the impact of noisy gradients. Okay, so the momentum itself, if we want to look at actually representing that with some math, then we can essentially use a linear interpolation between the previous value that we had for our momentum and the new value. And essentially, actually, it's not quite a linear interpolation. It's an exponentially decaying moving average. And so this exponentially decaying moving average, we can understand this by example. So let's suppose we parameterize B1, and B1 is our first hyperparameter for the Adam optimizer. Say we set that to 99%. So what our momentum is going to be for our next time step will be 99% of the previous value. So it's going to retain a lot of its initial momentum, but it's going to accept a 1% change in direction from the current gradient. So even if this is in completely the wrong direction, it only matters 1% as much as everything else up to that point. Okay, and so I'm actually going to simplify this here. There's a small note here, and it's about a correction term that's applied to our momentum, and that's just to correct the start of training. Because if we use this naively as is without introducing a correction term, then at the start of training our momentum estimate is going to be off, and it will take a large number of steps for that to correct itself. And so what's not shown here is a small correction term that we add in, but hopefully the intuition is understood. Okay, so let's talk about the denominator. Yeah.
Beta is a hyperparameter that you tune, or?
Yes, so beta 1, there's, Atom has two hyperparameters, actually, well, you could potentially consider like there's an epsilon parameter in there, but there are essentially two main parameters, one for the numerator and one for the denominator, and they essentially control the strength of these exponential moving averages. So if these, this is actually the default value for B1. It's typically set to 99%, and the other one's typically set to 99.9%. And essentially, it just says that like keep 99% of the momentum that you have, and accept each new training step, have that contribute 1% to the new value. So it really smooths things out. But you're completely free to modify these hyperparameters, and often what people will do when training is find better values than the defaults. So through a hyperparameter search, when you're looking through many different variants of your model, you're modifying these hyperparameters to find which ones result in a better overall model. And so, like for instance, I found for beta 1, for a lot of the GAN work that I've been doing, typically I'll use values either like 0.5 or 0.75 instead of 99%. But it really depends on the particular application, and it's something that can be optimized through a hyperparameter search. Okay, so the denominator here, that is our average recent deviation in the gradient. And so the denominator term allows the Atom Optimizer to slow training after entering an area of parameter space where the loss landscape becomes very steep. So, and the rationale behind that is that taking big steps is risky in steep terrain. So similarly, when a parameter enters a valley in the loss landscape, when the gradients really even out, and when the loss landscape is very smooth, then the denominator will actually have the effect of speeding up training for Atom. Because it's like you can run through valleys, but you should take small steps in steep areas. That's essentially the intuition behind it. Yeah, okay. So this gives us our form here. The denominator here, it is a exponential decaying moving average of the squared gradients. So it looks very similar to the numerator, except instead of just considering the gradient, the first moment, we're considering the second moment, the square of the gradients in the denominator. And this is going to have a larger impact for the gradients, right? If we're using the square of the value versus versus just using the gradient itself. So, okay. Our variance term here is used to regulate the learning rate based on the moving average of the squared gradient of the parameter. And the moving average is controlled by our second hyperparameter in Atom called beta 2. And this moving average is usually an order of magnitude slower to change than the momentum. And so, yeah, what I just had mentioned there is that beta 1, 99%, beta 2, 99.9% as default values. Okay, and so then we've got that represented up here. we're actually taking instead of the variance, we're taking the deviation, so that's why we're putting the square root symbol on it. And then our epsilon parameter there is just to put an upper limit on the amount of speed gain that we can get in shallow regions, and essentially to prevent division by 0, right? Okay, and then again, like before, because we're using an exponential moving average, at the start of training we need to apply a correction term, and so this note is saying, let's assume it's there, but it's not shown. Yeah?
Why is beta 2 an order of magnitude slower than beta 1? Like intuitively.
So
don't run across the valley until you're really sure it's a valley?
Yeah, so let's see. What would be a good intuition for why it would be faster for beta 1 to change than beta 2? So I would treat beta 2 as kind of a more like a longer view of how the gradients have been changing during training. So it's probably a little bit more accurate to say that there's different phases of training, where instead of it being like valleys and mountains and then valleys and then mountains again, usually what I've seen in terms of gradients is that they will essentially go through different phases, where often what will happen is the gradient will either continue to increase or continue to decrease through training. And so then this gives us a very smooth view as to what kind of environment we're dealing with there. Yeah, that's probably the best intuition I could give on that parameter. But it is a much slower moving average, generally speaking, than beta 1. I haven't seen any cases where beta 2 would be moving faster than beta 1.
Is it related to the fact that, like, if I want to look at the dimensions of beta 2 and beta 1, beta 2 is sort of the square of beta 1 in terms of dimension? You know what I mean? Like,
so beta 1 and beta 2 are just scalar values. And one thing to keep in mind, too, is that this gradient is with respect to each parameter here. So we're updating each parameter separately based off of these learning rates. So I'm not sure how to answer that question. Yeah.
We were talking about this a bit earlier, but there are a couple of papers, or there was one particular paper that came out, I think earlier this year, which was arguing that the denominator on the atom prevents it from theoretically converging. And that paper is apparently very popular, and it has to do with the numerator growing faster than the denominator. It's moving faster, so it's possible that you might skip your valley, or it'll just kind of explode the learning rate, or the gradient update.
Yeah, I totally believe that.
That being said, like you mentioned, Atom generally works very well in practice, despite that issue. Yeah,
so like in terms of conventional optimizers, Atom is usually top of the charts, right? Like, so now we're going to be talking about Eve, and that's, yeah, we'll get to that in a moment. But Atom is an extremely good optimizer to use, unless you need to fine-tune your model to the point where it matters. Like there's potential gains that you could get by further correcting Atom, and Eve is actually like a really awesome correction to Atom that yeah, we'll cover in a moment. All right.
Can I push a little for what I said?
Sure.
So let's say del t is 0,
yeah,
like the gradient of t is 0.
Right.
So the second term is going to be 0 in denominator and numerator. So essentially what you...
Oh, up here? So if it's 0 here, that would mean that we essentially, like our value that, that, assuming we're talking about 99.9%, our value from the previous time step will decrease a bit to 99.9% of
So what I want to say is that then in the expression that you have on the top right, the numerator is going to be beta 1 mt minus 1, and the denominator is going to be root of beta 2 bt minus 1.
Yeah.
So essentially the correction to your learning rate is going to be beta 1 over root of beta 2. So, and probably since you want to put these two on the same footing,
symbol over this. Yeah.
Right. Since you want to put these two almost on the same footing, so beta 2 should be almost an order of magnitude larger than beta 1.
Another point of view. So, generally, like V is trying to just measure like the curvature of the function. I think generally, like in terms of being able to fit second order terms to functions, generally curvature is much closer to being constant. So if you're, so this is basically, this is a differential equation that's trying to follow the real, like, you know, if something's changing more slowly, you can actually get away with having a beta that's way closer to 1, so way smaller decay of the roll of history, as opposed to like the gradient that could be potentially much faster changing. So the second derivative is generally, once you're within like a basin of attraction, is generally very close to constant. So you don't need like fast dynamics to follow the second order derivative, the second derivative, as opposed to like the first, the actual derivative that could be just changing linearly. I mean, I'm talking second order approximations.
And that, like one approach that I think might, like one intuition that might help with this, so by having beta 2 an order of magnitude slower, that essentially means that that this denominator is going to evolve much more slowly, kind of like the tides, right, in the ocean, whereas the waves in the ocean are they move much quicker than the tides, and we can describe that like maybe one way that might help think might help describe this. If we have a much more stable base here, the numerator is going to be moving a lot faster, so its waves are going to be much more significant, whereas this bottom term here is going to be more like the tide, that sort of like a change it scales the momentum in a much more gradual way through the course of training.
And in a way, like if you're like doing sum of square losses, we could argue that what beta 2 is tracking is much slower moving than what beta 1 is tracking. So yeah, we can get away with like being way more, having way more like inertia in tracking V as opposed to N.
Yeah, and the other thing that the fact that we treat beta 2 that way also tends to suggest that what matters more here is the momentum for training. So what immediately matters is the momentum, and that needs to be much more reactive than the sum of square gradients there. Okay. Okay, so now we have Adam here. That is the simplified formula. And we've got Eve, and Eve adds in a correction term. So this dt, let's take a look at what that's all about. Okay, but you can notice that otherwise they're entirely identical. It's like Eve is just a small evolution of the Adam optimizer. Okay, but this term is really special. Okay, so that's our new term. So with Eve, we dynamically adjust the learning rate based on how close we are to the objective. Okay, so some of the intuitions behind Eve. A large variation in the loss between time steps should be given less weight, and so a smaller step should be taken. So if we suddenly take a very large, if we suddenly see a very large change in our loss function, probably pay less attention to it because it's probably more noise than anything. And then if we are, the other intuition is that if we are very far from the minimum, then take very large steps. Okay, so a large variation in the loss between time steps means that we should be taking smaller steps. And so what we want is our dt term to be, our new term, we want it to be proportional to the difference between the loss at the current time step and the loss at the previous time step. So dt is going to be larger when the difference in our losses from the current time step and the previous time step are large. Okay, our other intuition, if the current loss is far from the minimum, in this case indicated by L star, then take big steps. And so we want our dt term to be inversely proportional to the distance between our current loss function and its possible minimum. And so we can just put those together. Yeah?
Good question. Generally what we are solving here is not convex. So how do we know L star? There's no like duality formulation.
So the paper references this, and this is also something that you can design too. If you think of like mean squared error, the bottom of that valley is 0 by design, by the choice of loss functions that you've introduced. And so in many cases, you can design loss functions that have a minimum at 0, and so this becomes much simpler.
Yeah. So doesn't that depend on how you regularize though? If you regularize the bottom like energy level might not be 0 exactly, because that's what you were kind of forcing. So I'm just wondering.
It's a good question. So the question being, if regularization is introduced, say L2 regularization or something like that, is introduced, then that is going to change where the minimum is in that loss landscape, which could be biased off of 0.
Yeah.
Yeah. That's a good question. So the authors of the paper just say, for their purposes, they've just assumed 0 is the minimum. And it could be interesting to find cases where it shouldn't be 0 and should be something else, because there's a potential that that could result in better performance. So it would be worth checking out it to see if that, like that definitely is an open area of research. Yeah.
So I have a controls background, but a lot of this seems very similar to like Kalman filtering and PID.
Yeah.
Why, why can't you just do a Kalman filter?
So why can't you just do a Kalman filter? So my understanding is that Kalman filters are a way to take into account time delay and to mitigate the effect of noise in the measurements, something like that, right?
Yeah, process and measurement noise.
Right. Okay. That's it's interesting. So I would need somebody from that field to be able to map map that analogy.
So it's so what you have is you have a state space equation, right, where you have sort of like all your parameters, and then you have like your y's as well. Mm-hmm. And what it does is that you have then a model which your you make some measurements, and then you have two routes. One, there's a model that predicts what the next step is going to be, mm-hmm. right? And then you measure it, and you compare, okay, how far off was it? And then you update your predictive model, and you keep going through this loop over and over and over again. Mm-hmm. So if you applied that same to this.
But that's another iterative, so you're adding just another iteration to already a few iterations that we're going through, right?
Yeah, I'm like Kalman filters are taking a predictive step ahead, essentially.
Yeah, they're taking a predictive step ahead, and then when you make the measurement at that next step, say like for example, like in the loss function, you have your y that you predicted, and then there's like y that was actually measured. So then the y that's you would have one step where it's like the y that's predicted the next step, and then there's the y that's been measured at the next step. You're taking kind of like the difference between that, and you're adding that back into the model. I'm also not a mathematician, so maybe I'm not explaining it right. But it's like I just see just a lot of these concepts mm-hmm. from like data science, and there's so much connection with control theory. And if people just looked at control theory and took the math from control theory, I think it would solve a lot of data science problems.
I think that's where you're getting wrong, because the thing is that people do look at control theory. Okay. In a lot of control theory, there's adaptive control, where it's all about applying machine learning control mm-hmm. theory, and vice versa. So a lot of these thoughts may have potentially come from other fields, and it's usually the case. Sorry, Alex, did you want to speak?
Yeah, just to make a comment, there's like a simpler variation of filtering, like linear filters. They're basically very similar to this. Like common filters are like almost second order, because there's like there's a non-stochastic picture of common filtering that is called RLS, recursive least squares, but which is kind of again like second order. I don't know, like this is very confusing because this is almost like 1.5 like order optimization, because you're doing a lot of running sums that are kind of could be effectively like a conjugate gradient, but I don't know, like it's I agree with you. It's very similar to a lot of things that people do in like Kalman filtering, linear filtering, and stuff like that.
Because like I mean, in practice, like do you then play around with the d values and the alpha and then the beta, and then you just like plug and play different numbers, and then oh wow, now I got like a much accurate number. Is that how it works? Is that how ultimately it's supposed to work? Oh, okay.
Yeah.
Well,
okay.
In this particular case, so this is going to further evolve in the upcoming slides. But so far what we have is calculated terms, like the loss is just a calculated value. But how we calculate that loss, there's a lot that can go into that. Mean squared error being like probably the simplest example that I can think of right now, but loss functions can become arbitrarily complex, involving all different types of stabilizations and so forth, and optimization criteria, potentially even multitask objectives and so forth. Yeah.
Quick question. I'm just confused about the zero. I mean, there is no assumption that the minima has to be at 0. It can be anywhere, right?
It could be anywhere, but you have the choice to design your loss function.
Yeah.
And in many cases, you can just choose a loss function that has a minimum at 0.
Yeah, but I
or
guess the algorithm,
close to 0.
Algorithm has nothing to do with that. I mean, it would work no matter where your minima of the basin is, wherever L star.
Yeah, so if you have a way to actually calculate what L star is.
Yeah, that's probably you don't have, right?
Yeah.
The problem doesn't mean, if you don't have like duality, how do you know what the optimal value is without solving the problem in the first place?
So I would say empirically at that point. So if you begin training your model and then observe that the loss function is converging towards 0, or maybe it's converging towards 32. If it's converging towards 0, throw in 0. If it's converging to 32 and it looks like it's, you know,
like a chicken and egg problem. Like how do you know your optimization algorithm is
Well, you don't exactly. You don't have to do this in one shot, right? So you could start with the atom optimizer, get a feel for your model, measuring the measuring how the loss is changing over time, like log it as a scalar in TensorFlow or whatever, view it on TensorBoard, and then you should be able to see at that point like what kind of domain you're dealing with your L star. And so if it seems pretty clear that like, okay, yeah, I could throw in and it might even be something by design too, right? Like you could say, for example, if we think of a designer loss function where we say that we want like the value f of x from our model to, like, if we throw that into a loss function where we're like f of x minus 2 squared, and we want to minimize that, it's going to minimize when f of x reaches, well, in that case, is 0 as well, actually.
So the problem is this, yeah, if you want to set L star uniformly to 0, I'm totally okay with that. In this case, but like if your algorithm, if your optimization algorithm is plateauing somewhere that is not the real minimum,
that's true.
You're basically like shooting yourself in the foot. You're not going to get any better than that, because as soon as you get close to L star, this is going to go to 0.
Mm-hmm.
So yeah.
Actually, I would like to add something to this 0 thing, that whether it is at 0 or at different place, different point. So it is property of the space in which this is happening. If the space is homogeneous, then every homogeneous space means where these functions are defined, right? So if the space is homogeneous, then any point of the space can be considered as origin, means 0.
No, this is the value of the function. This is in the range. This is not the domain.
Yeah, exactly.
Homogeneous.
So by scaling, it is possible. By scaling, it is possible to set any point of the space as origin, right? For example, some homogeneous space is there. For example, the simple Cartesian coordinate system. So you can take any, suppose you want this point, this is your 0, then you can scale such that it is your 0, and you can design the whole procedure.
Mm-hmm.
So it is possible. That one thing is there. And another thing about the dual space, you said something, right?
Not dual space, like duality in optimization. Like
Duality in
Lagrangian
so it is already in the theory of optimization, convex optimization there, that if these spaces are this comes in functional analysis, perhaps the pure mathematician can elaborate more about this. So in which functional analysis there are Banach spaces, and all these problems are of Banach spaces where dual space exists.
There are Banach spaces, but the problem is most of these problems are not convex optimization problems. If they were convex, like I don't know, conjugate gradient would be 100 times better than any sort of stochastic, like first order method. So that is the problem in neural nets. If you knew for sure that your function is convex, then you wouldn't do this. You would actually do like some sort of preconditioned conjugate gradient.
Yeah. I would edit my comment that these spaces are Banach spaces, and that part is for the dual space part, right? So for them dual space exists, and so the whole theory that LT and L star is mentioned, it is existing there.
No, but so what I'm arguing is way simpler. If by some fluke of chance the value that I think is the real value of L star is not the real value of L star, so you said like empirically, I've determined, but my algorithm is pretty shitty, so it plateaus at some L star that is not the real L star. So I would just shoot myself in the foot, because this is again going to go to 0 as soon as I get close to that L star. So it's not going to converge any further. So it doesn't give me any visibility into what is possible. It just kind of limits me to what is already there. So actually 0, in my opinion, is like a way better choice for L star, because at least you know, I mean, if your loss is positive, which most of them are, at least that's like a lower bound, so you're not going to ever get close to 0.
Yeah, and so that's exactly what the authors in the paper essentially said, is that like that because they can't know what the true value of L star is, like what the minimum the model would be able to achieve, like in theoretical terms, like we could see what the minimum value of a loss function could be, but is it possible for the model to find a parameterization? Like, is it possible to find a parameterization that would result in that minimum value? Or is there a minimum that is limited by the choice of neural net? Maybe your neural net is too simple and isn't actually able to reach a true value of 0. So its actual value of 0 is potentially elevated above 0, and for the sake of example. And so that could potentially cause issues here, but the authors in this case have they just took the approach of saying that, like, while there probably is a floor that's not 0, but for the purposes of the paper and for the implementation, they just went with they said we'll keep this here. This is like part of Eve, but if you don't know what to put there, try 0. Yeah.
Super low sophistication question. Your labels are reversed, right? I'm not totally confused.
From the previous slide?
No, from like the numerator description should be the denominator, and the denominator description should be the numerator.
So this term here, this is
just the descriptions with the arrows, the boxes.
Yeah, she's right.
Oh.
Yeah, you said you wanted LT minus L stars, if you're right.
Yeah, the arrows are kind of.
Okay, somebody is paying attention. Correct.
Yeah.
Okay.
That was by design.
In case if that wasn't true, it meant that I was really lost.
He was checking our learning rate.
All right. So in the numerator, we want to take big steps when we are far from the minimum. However, this is at risk of a positive feedback loop. So if LT increases, then our step size increases, which can take us even further from the minimum, which increases the step size, which takes us even further from the minimum, and so on, and so on. And so then our network explodes. Yeah, it's unstable. Okay. Hello? What was that? Is everyone still here? What can we do now? Our network just exploded. Well, it exploded, so let's clip the new term so that stays in a bounded range with a ceiling of C and a floor of 1 over C. Great idea. Let's also add smoothness to DT with another running average. So we already have 2 of them. Let's add a 3rd one in there just for fun. Yay! Okay, sounds great. So
is that actually generated by chatbot?
Okay, so that's Eve, essentially. There's those additional terms, and I mean, it's, okay. So let's take a look at some of the experiments. So this is Eve compared to, this is taken directly from the paper, by the way. This is Eve compared with atom, atomax, RMS prop, adagrad, adadelta, and stochastic gradient descent. And in this case, I think this was on one of the CFAR tasks there. So we can see that Eve just totally rocks it. Yeah, and then here we've got a zoomed in image from a separate experiment here where Eve was slightly underperforming atom in this particular case and atomax, but it is still in a really decent range here. Here it totally rocked it. Okay, so now let's also compare this with decay strategies. So we were talking earlier about exponentially decaying it, or decaying by 1 over t, or 1 over the square root of t, like t being the time step. So gradually slowing down the learning rate. That's a very effective strategy. And so just comparing the two, we see that Eve, again, outperforms versus a standard approach of just using it at a decay with, I believe in that case they were using, I would have to refer to the paper, whether it was atom or stochastic gradient descent. But one of the things that they called out here is that they found that atom with different exponential decay strengths has a wide range of variation, whereas Eve, by dynamically adapting, outperforms without having to choose the right decay strategy. So if you want to use gradual decay, one of these strategies here, you need to be able to parameterize that, choose the decay strength. And so finding a good choice for that can have a dramatic impact on the performance of your model. So if you don't want to spend time doing that, use Eve instead. Okay, and so there is a GitHub here called Deep Learning Implementations.
Sorry, can I ask a question about the previous slide?
Yeah.
Did you talk about like the different decay choices at all, or are these related to beta in any way, or is that a completely different?
So decay strategies are where, if we look back at, okay, so here we've got atom, and Eve is very similar here. When we look at the learning rate parameter, this learning rate parameter here is just a scalar value that what's represented here is a fixed value. But you have the option to change that. Instead of it being alpha, you could have alpha sub t, where it's dependent on time. And so you could have alpha be essentially a function of time, or a function of the number of steps into training. In terms of having a decay strategy, so it's essentially like a programmed rate of decay, where you could say decay exponentially, or based off of the inverse of the number of steps into training. Cool. All right. And so if we run through that quick conversation there, and okay, there is a Keras implementation of Eve that is available. So if you've been creating neural nets, you can start using this right away. This is on deep learning implementations. They do this kind of thing with a lot of papers, and they also have a number of other experiments where they've documented the results with Eve, and it does very well as well. Okay, so thank you. All right.